Welcome to today's video. Today we start the final block of the course on general relativity proper. Nice, we made it here. So, similar to what we did in special relativity, today we're going to set the basis on which the theory rests. We're going to lay out the postulates of the theory. Now, this is kind of going through the same steps as Einstein did. Let's begin with the reason why we want to think about gravity in a geometric way, which is the topic of postulate 0. There's something called the weak equivalence principle. The gravity is really weird. Newtonian gravity is really weird. There's something funny with gravity. When you write mass, let's say inertial mass, to call it that, times acceleration, Newton's second law, and then you have a force like the electric force, right? You have E, then you have some Q, then you have some constant K divided by R squared or something like that. Then this is the charge of the particle that you're considering. This is the mass of the particle. So the acceleration certainly depends on the mass, the inertial mass of the particle. And makes sense because the inertial mass is the resistance to be accelerated by any force. All right. But there is something funny about gravity, right? Gravity, if I write the case for gravity, I would get here the gravitational mass, then M, then G, then R squared, and then MI. And the problem, the issue that we have here is that the gravitational mass and the inertial mass seem to be the freaking same. And that is ridiculous because they do cancel. They do cancel each other. So the acceleration that you experience does not depend on your mass. It's like saying the acceleration that you acquire on an electric field depends on your charge. Obviously, the stronger I couple to the electric field, the stronger I will be accelerated. Not in gravity, not in the case of gravity, no. The larger your mass, you still feel the force with the same intensity. And that is ridiculous because that means that even in the limit, when the mass goes to zero, you still accelerate. Newton, and at the time of Newton, people already thought of, oh yeah, light's certainly affected by the gravitational field. We can even talk about black stars, they said, which is stars that are so massive that not even light can escape from them. This is very funny. This is what we call the weak equivalence principle. And it's really, really weird. That also means that I'm not able to distinguish a gravitational field from an acceleration because it affects everybody. Like, let me put it like this. Two scenarios. In one of them, I have some sort of elevator, right? That is accelerating. It's accelerating upwards. So in the non-inertial reference frame of this person, there will be forces. Well, something that looks like gravitational forces, which is because the system is accelerating. And you would feel them and things would fall because you're accelerating. And oftentimes this is called fictitious forces. Fictitious, I don't know, fictitious, no way. Fictitious, those things would crush you. They would kill you. Oh, but don't worry, they're fictitious. They're not fictitious. Well, I mean, they're called fictitious for a reason. But what I mean is that they are very real. They will destroy you if you give them the chance. Those forces, they're called fictitious because you're not in an inertial frame, and therefore you see them because you're in an inertial frame. But you are freaking in the freaking non-inertial frame, and those forces would kill you. All right? So don't underestimate those forces, please, ever. Point being, in any case, that this scenario, right, is difficult locally, is indistinguishable from this one, in which I have a box that I hold with some like bars or whatever, and I'm here, right, in this box. And I feel the gravitational field because there's a mass, there's a center of gravity, there's a mass. So locally, I can't distinguish the presence of a gravitational field from the presence of an acceleration. Of course, no locally I can. In this scenario, you see the acceleration go down. If I have two balls here, they would actually fall towards the center of gravity. Well, it was the center of gravity. Yeah, I kind of not did it the best way possible, but you see what I mean, right? They fall towards the center of gravity. So they would get closer to each other as they fall, right? So as opposed to this one where they actually go horizontal. Anyway, that is a different story and we can discuss it. Non-locally, you can distinguish an acceleration from a gravitational field, but locally you can't. And that's what we call the weak equivalence principle. So because this equivalence principle that everything seems to be accelerating under a gravitational field regardless of the mass they have, the mass you have, then this kind of suggests that perhaps gravity, there's something geometric about gravity. I mean, you could have done it without relativity, right? Newtonian gravity already suggests that. And in fact, you can formulate Newtonian gravity geometrically too. That's called the Newton-Cartan theory. Now, Newton-Cartan has its own issues. If you don't do it Einstein-like, you have your own issues. And in fact, there's something with 4 reasonable assumptions in Newton-Cartan that are mutually incompatible. You have to give one up. Actually, one of them is the existence of a global universal time function. So the absolute time, no set of absolute time to be able to do it. So maybe that's the way we would have reached eventually general relativity if Einstein hasn't been there. If Einstein hadn't been there, I think that's probably the way we would have arrived to general relativity, but probably many years after Einstein though. Anyway. So, yeah, you see the inspiration. Gravity is weird. It seems that everything accelerates the same way in the presence of a gravitational field, and therefore maybe there's something geometric about gravity. Then Einstein said one day, well, if I'm going to have to describe gravity geometrically, I better learn geometry. And then he spent years learning differential geometry in order to be able to formulate general relativity. All right, let's see what the postulates, the formulation of those postulates is. And let's begin with postulate 0, which is about precisely the ability to formulate gravity geometrically. All right, postulate 0 tells me that space-time, the set of all events, can be modeled by a differentiable manifold. This is just saying gravity has to be geometry. And then you say, well, gravity is understood as curvature of that space-time manifold. Gravitational forces result from geodesic deviation of the free matter fields moving through space-time. So very simply, postulate 0, this is again where it all begins. It's saying gravity has to be geometric. And therefore, we need to be able to formulate in terms of objects of differential geometry. All right, wonderful. So now let's flesh it out. Einstein didn't come to general relativity out of nowhere. Einstein did special relativity first. So postulate 1 is about saying special relativity has to work at the very least locally. So let's see what constraints it puts on the geometric description of gravity, the fact that special relativity has to be true locally. That's postulate 1. All right, so postulate 1 tells us that space-time is not any differentiable manifold, it's a pseudo-Riemannian manifold. Remember, we have a metric and we have a connection compatible with the metric that gives me the covariant derivative. Now, this is the Riemannian manifold M with a Lorentzian metric. So in particular, I wanted to have a Lorentzian metric. This is to support the compatibility with special relativity. Modulo isomorphisms, which means that more specifically, that means the modulo isomorphisms means that 2 pairs of manifolds and metrics, Mg and M prime G prime, represent the same spacetime if and only if there is a diffeomorphism that takes me from M to M prime, such that the pullback of theta acting on G takes me to G prime. So basically, that means that general relativity will have something called diffeomorphism invariance, or for the friends of the theory, diffeo invariance. This is the fundamental group of symmetries of general relativity, and it does generalize the group of symmetries that you would have in special relativity. The demand of diffeomorphism invariance is because those are the transformations that will map in general relativity solutions of dynamical equations to solutions of dynamical equations. Those are the transformations that will leave the laws of physics invariant in the context of general relativity. We can discuss more about the group of diffeomorphisms and the role they play in general relativity. Let me tell you, it's non-trivial. There are many claims that very important people have made that are, kind of controversial in many ways, as in like, what is different about general relativity that other theories don't have? And some people point to the diffeo invariance of GR. Philosophers of physics tend to disagree with that. Anyway, we can discuss that in a live session if you want. But then again, this is precisely the set of transformations that map, that leave invariant the equations of motion in the context of general relativity. All right, let's move to the part that gives the name to postulate 1. The postulate 1 is the postulate for local causality. The equations of motion of matter fields have to be such that 2 given points in a convex open subset of spacetime are allowed to exchange signals if and only if they can be connected by a causal curve. That is, a curve whose tangent vector is not space-like at any point. What does that mean? Well, that means, let me just translate directly what it says to plain words, and then we translate to a single plain sentence. This is telling me that if I have 2 points in spacetime, they can only influence each other, they can exchange signals, only if the curve that joins them is always time-like or at most no, but never space-like. The tangent vector will never be space-like. That's basically telling you that the physical trajectories are either time-like or light-like. And remember that that is exactly what we had in special relativity. As a single sentence, this postulate is telling me that special relativity should work locally. So let me summarize a lot.
Special relativity should work locally.
Right? We have the structure that we have in special relativity at every point. So basically we're saying we have light cones at every point in space-time. Every point of space-time has light cones. So there's a way to tell, like if that point of space-time I'm moving time-like, light-like, or space-like, and I don't allow physical trajectories to be space-like. So this is telling me I want to keep, special relativity works, except for in the absence of gravity. So it makes sense that locally it has to work. We need to have special relativity as a particular case, if you want, of general relativity, and in particular we want to have it locally. Locally, where I don't see the curvature of space-time, locally I should have something flat, I should have something like special relativity. So this is an important postulate that tells me how special relativity is baked into general relativity. And again, that's why I need to demand a pseudo-Riemannian manifold, that's why I want a Lorentzian metric to be able to support locally special relativity. Locally, at every point, the special relativity that you have at every point is different. And how you move from one to another is precisely what makes that different, what makes general relativity general. Alright, so postulate 1, local causality, special relativity exists locally. Before moving to postulate 2, let me give you a dirty recipe. Dirty recipe is a consequence of postulate 0 and postulate 1. It is a recipe of how to go from special relativity kind of covariance to general relativity kind of covariance. If you have a law of physics, remember that laws of physics, or most laws of physics, are local. So if you formulate a physical theory in special relativity, the translation to general relativity can be pretty easy. If you have something that works locally, we know that special relativity works locally. So write your covariant equation locally and then do the transition of from the flat metric, go to the full space-time metric with its curvature, and from the partial derivative, go to the covariant derivative, because remember, the covariant derivative for a flat connection is the partial derivative. That means that if I have an equation of something, say a fluid, a field, whatever I want, and I know it in special relativity, making the general relativistic version could be pretty easy by doing this, okay? Albeit being careful with some things, right? Because the determinant, the minus determinant of this metric is 1. And sometimes you have to substitute the minus determinant of this metric by the determinant of minus determinant of this metric, right? So it's not as clear-cut as I'm really portraying it to be. But as a general rule, this is a pretty useful rule of thumb. Just change the flat metric to the curve metric, change the partial derivative to the covariant derivative. Find the equation to be covariant in special relativity. If it's easier for you to do in special relativity, how do I generalize it? Generalize it like this. It's a dirty rule. So we can discuss it also in the live sessions. All right, let's move to postulate 2. All right, postulate 2. We will call this one local conservation of energy and momentum. So the postulate says, the equations of motion of matter fields are such that there exists a symmetric tensor, TAB, that we will call the stress energy tensor, built from the matter fields, its covariant derivatives, and the metric tensor. Those are the only ingredients I'm allowed to have. Such that its divergence is 0, which means this is symmetric, so it doesn't matter. This is the divergence of the tensor. And such that it is 0 in an open set if and only if the matter fields are 0 as well. Alright, so what is this postulate? What does it tell us? So this is postulating the existence out of whatever matter fields are. It could be a particle, it could be the electromagnetic field, it could be dust, it could be people. Whatever we have as matter, we postulate that there exists some quantity, TAB, that you can make out of the matter fields, the covariant derivatives, and the metric, such that it is divergenceless. Now, why? This is the analog. So if we look in special relativity, this is the analog. Think of Gauss's theorem. This is telling you that there are no sources or sinks locally. So if you have a volume surrounding some area, there are some quantities within the matter fields, characterized by the matter fields, that the amount of them that enters the region, when you integrate over it, equals the amount that exits the region. Therefore, that means that there are no sinks, and there are no sources, right? This is basically postulating that you're going to have some generalization of a continuity equation. Matter fields are such that they kind of just disappear. They have to have something that kind of just fall into a sink or be created out of a source, all right? This is what this is telling you. Locally, we can associate this to nether currents, to conserve quantities associated with some flows. TLDR, this postulate, is telling you that with the matter fields you can build something that is locally conserved, all right? And this is very reasonable because we have that. In fact, in special relativity, we will have the equivalent with divergence, as you know, with the partial derivative. This is the generalization of that principle of conservation. Now, this postulate doesn't tell you what the stress energy density is. It just tells you that it exists. It's your mission, given some matter field, to find the stress energy density. Now, of course, we know how to find it for simple cases, like for a particle. We know that for a particle or for like a beam of particles or something like that, this is going to be the divergence less of the flows of the momentum and energy and things like that. This is the generalization of the stress tensor in continuous media in fluid mechanics. So in general relativity, we know that in special relativity, we will know how to build it. In mechanics, in Newtonian mechanics, we know how to build it. We just postulate that it exists for general relativity. How do you build it though? Well, if you know it in special relativity, you just upgrade the partial derivatives to total derivatives and the flat metric to the full-fledged metric, and then you get it. That's a good, the dirty trick to do it. But important, this postulate only tells you that you postulate matter, you should be able to build some conservation law. You should be able to build some local continuity equation out of the matter fields. And this is what we're postulating here. Now, something interesting to notice, if you remember, we discussed when we were talking about conformal transformations, that defining the causal structure of a Lorentzian manifold, defining what, for all the points in the manifold, defining what points are time-like separated from it, null separated, or space-like separated, fully characterize the metric except for a conformal factor, right? So in a way, given the causal structure, what is kind of fixing in postulate 1 would determine the metric up to a conformal factor. Now, one can prove, and that's actually a pretty cool exercise to do, that demanding that the divergence of the stress energy density is 0 for a particular metric means that it won't be 0 for any other metric that is related to the previous one by a conformal factor. So fixing the stress energy density fixes the conformal factor indirectly. As like, oh yeah, this is the stress energy density and it has to be divergence-less. That fixes the conformal factor of the metric. If you have the causal structure and you have a stress energy density, you have the full metric as well, because it determines the conformal factor. Of course, except for a multiplicative constant, which is the physicist's freedom to have units, which you always have. I mean, thank goodness that we can choose units, right? You always have to have this freedom of choosing your units. All right, so this is postulate 2. There are always those among us that are looking forward to one point in a course of general relativity, which is the point where we actually derive Einstein equations, right? It's nice to see the derivation of Einstein equations. Even some people would even say that they've seen already the derivation of Einstein equations, right? All right, the time to get Einstein equations has arrived. Postulate 3, Einstein equations. What? Einstein equations are not derived. The equations, these equations here, are satisfied in the whole space-time. Postulate. How you feel about that? Okay, so you see, sometimes people would say, but I've seen it derived. Look, they start from something called the Hilbert-Einstein action. It's the same thing. Postulating the Hilbert-Einstein action or postulating the equations of motion is equivalent one-to-one, as we know from, mechanics or our previous videos in special relativity. Out of an action, I get equations of motion. I can postulate at the level of the action, or I can postulate at the level of the equation of motion. For completeness, let me just say that, of course, actions and equations of motion are not one-to-one. I can add extra terms to an action that have no relevance and don't appear and don't affect the equations of motion. But we consider basically the same physical theory, those actions that actually yield to the same equations of motion. And in our case, postulating the Hilbert-Einstein action would be exactly equivalent to postulating Einstein equations of motion. Like always, there are always subtleties, and I will be very, very happy to discuss them in our live sessions. Let's go back to the video. So, yes indeed, the Einstein equations are not derived as a consequence of other things. They are a fundamental postulate. And then we can wonder why Einstein postulated these equations in particular and not other things. because really. All right, let's talk a little bit about it. The equations, and this is the Ricci tensor minus 1/2 of the Ricci scalar metric tensor plus some constant multiplying the metric tensor equals 8 pi g divided by c4, c to the power 4 stationary density. And the postulate is that these equations are satisfied in the whole spacetime. Now, where did they come from? Where did this equation come from? So Einstein thought of the following. I need to have matter on one side of the equation, sourcing gravity, and then space-time on the other side of the equation in a way. I mean, I'm simplifying a lot, right? But follow with me. Right. If I have matter on the right and all that I postulated about matter is the stationary density, then I know that the right-hand side is divergenceless because the stationary density is divergenceless. So I need to find a divergenceless tensor that is made out of the ingredients of space-time, which is the metric and the curvature, right? And the curvature tensors. So Einstein starts thinking, okay, what is the simplest tensor that is divergenceless that I can build? Well, the simplest is just the metric. The metric is divergenceless. The covariant derivative is compatible with the metric. So you can start like that. But that's too trivial. Okay, what's the second simplest? This is the second simplest. This is the second simplest. Right, let's postulate it. And you postulate it, and it freaking works. It nails the experiment. In fact, so far we just keep finding that Einstein's predictions were good, and now we can see black holes, like you can like focus telescopes on black holes, still everything works. This is a really, really good guess. Now, there are infinitely many ways in which I can choose this side. I can make it more complex. I can add extra additional powers of curvature. I can have contractions of the Riemann tensor. If we were to add those terms, we would be on in a realm of theories that we call higher curvature gravity. And indeed, people have studied that. But it so happens that there's strong evidence that the one that works is this one. Adding complications doesn't improve anything, makes it worse. So this is really a good guess. And the guess comes from the consistency of the theory. Having matter, source, gravity. And I need a divergenceless tensor here, I need a divergenceless tensor here. This is the simplest non-trivial one. Now, there are some arguments that tell you that this should work in a way, but those arguments are at best tenuous. Certainly they could have. You don't have a good reason to discard a priori higher curvature terms in here. They just don't happen to be there. Experiment tells us that this is what works. All right. Einstein did some consistency checks as well, and but then again, he didn't discard that there could be higher terms. It was later on when people studied. Rodman has done a lot on higher curvature. If you want to ask somebody that is extremely knowledgeable on that, on higher curvature gravity. All right. Let's understand also this term here. This multiple of the metric was actually originally not put there because, again, it's a complication that we may not need. Einstein didn't need it to explain the things that he wanted to explain, but he added it because he started thinking about cosmology. And in fact, Einstein tried to explain the fact that, well, I mean, if I actually do cosmology with this kind of stuff, looks like the universe is going to be expanding. Einstein didn't like that, had biases and prejudices against it that he confessed later on that were biases. And said, no, let me add a term, and that term will actually hold gravity down and prevent that expansion to have a static universe. Turns out that Hubble found, and other people found that the universe is actually expanding, so Einstein was like, no. Imagine Einstein could have predicted the expansion of the universe with a simple proposal like that. Maybe he would have won another Nobel Prize in Physics before Jean Bardeen, but no, that didn't happen. Nowadays we keep it because it turns out that the universe is expanding at a rate that is faster than we thought. It seems to be accelerating its expansion. So we need actually a wider universe in terms of the expansion. We will talk more about that because we're gonna do, one of the videos that we're gonna do is an exercise, solving an assignment exercise of previous years that is about building cosmology from scratch. We start from the cosmological principle. The universe should be homogeneous and isotropic. And from that, we will derive the Friedman-Robertson, the Lemaitre, Friedman-Robertson-Walker metrics. We will derive the Friedman equations, etc., etc. We will do that in a video. That was actually an assignment. I think a pretty cool assignment, in my opinion. But then again, I'm biased because I'm the one who gave it to people to solve. Anyway, we'll do it, and we will see cosmology, how we build cosmology from general relativity, and we will talk more about this little bit here, about what it implies and things related with energy conditions and things like that. But we need to wait for now because we don't know enough to delve into what that means. All right, so we have seen the three postulates, well, the four postulates, 3 + 1 postulates of general relativity. I hope that we have a big discussion about them in the live sessions because, as usual, the postulates is what we start from and take for granted from first principles, and then we build our theories on top of that. By the way, one of the most effective theories that have ever been created in terms of like it's been valid for a long time, and all these predictions, the one observed and the one not observed, have been found experimentally time and time again and confirmed. So yeah, I mean, and it's funny because general relativity predicts its own demise. General relativity tells you itself, no, I'm not a good theory, I'm not a complete theory, I fail sometimes. But when it doesn't fail, it's amazing. And when it fails, it tells you, what else can you ask from a theory? I think this is the best. You can ask, I cannot ask more from you. Thank you, theory, you've given everything to me. Before we move forward, let me introduce the notion of natural units. Natural units is what we're going to be using from now on till the end of the course. Natural units are extremely convenient for everything. They are, you see, the systems of units that we have were developed for societies that barter with chicken, not for societies that wanted to understand the universe. If we wanted to understand the universe, the right system of units to pick is natural units. Now, again, what is the difference between a system that is dedicated to chicken bartering to a system that is dedicated to studying the universe? Natural units get all the fundamental constants, but one typically, and make them equals to 1. So C equals H bar equals 1 with our units. That is kind of nice because that allows us to, so the units of time are the same as units of length. Kind of makes sense because it makes space-time. It's nice that they have the same units. And then length is energy minus 1. You can talk about the frequency of a photon if you want. What is that? Oh, H bar omega. Omega is seconds minus 1, it's time minus 1, right? Oh, right, energy and time minus 1. If H bar is a dimensional on 1, that's the same. And also mass, mc squared, right? E is equal mc squared. So what you do when you pick natural units, you pick one unit. For example, I want to express everything in natural units of length. And I can express everything in terms of meters and powers of meters if I want. So if picking one scale, and everything else is relational to it. Don't confuse natural units with Planck units. Planck units makes also G equals 1. Planck units is remarkably bad in my opinion for doing these kinds of physics, because in that case you don't refer everything to one scale, everything is dimensionless. So you lose the real difference between one magnitude and another, right? In natural units, when you find things that have different units, genuinely different units, it's because they are different things, they're unrelated. But if you get, for example, mass, energy, or linear momentum, all those things are kind of different manifestations of the same thing in relativity, like time and space. How much time and how much space, well, that depends on the observer. How much energy, how much momentum, that depends on the observer. See what I mean? The units, the things that have the same units, is because they are kind of the same thing. And things that will have different units are truly different. So keeping one scale and referring everything to one scale allows us for two things. For recovering proper dimension full units whenever we want, and also to be able not to lose track of what their different magnitudes are. That is different with natural units than it is for Planck units. I would not recommend to use Planck units. Planck units, you also make G equals one dimensionless. Planck units, yeah, sure. I feel the philosophy is similar to natural units. If I were designing a universe, I would take all the universal constants equal to one dimensionless and then let it run. But in Planck units, you actually lose the distinction between, because everything is dimensionless in Planck units, you lose the distinction between the quantities that are different scaling, right? So I prefer much better natural units than Planck units. And for this course, we're certainly going to use, for relativity it gets confusing with Planck units. For relativity, natural units are the best suited by far. And those are the ones we're going to use. Now, let's explain a little bit the natural units. For example, if I ask you, what are the units of G? The Newtonian gravitational constant. Well, the Newton's gravitational constant. Well, we know, I mean, there are many people from Astro looking at these videos and you know what the dimensions of G are, right? We know that they are like this. But of course, in natural units, length and time has the same dimension and mass has a dimension of time minus 1. So the resulting dimension quantity, if we, depending, do you want, let's do it, we can do it in natural units of length. In natural units of length, the units of G are L squared. In natural units of time, the units of G are T squared. In natural units of energy, the dimensions are energy minus 2. So we can express G in meters squared. We can express G in seconds squared. We can express G in joules to the minus 2. All these things are valid units for G in natural units, depending what we refer it to. Natural units usually connect with the fundamental values of some things. Let's do an example. Let's do an example with Earth, like the parameters of Earth expressed in natural units and what they mean. All right, let's convert to different kind of natural units. This quantity is related to Earth. Well, this is the radius of Earth, this is the mass of Earth, and this is the gravitational constant. So let's do a conversion. Let's start with the radius of Earth. The radius of Earth here is already expressed in natural units of length. So if we want, those are natural units of length. We can convert it to natural units of time. Very easy. Like that. So the radius of Earth in natural units of length divided by c, I get it already in seconds. So r divided by c is 0.02123 seconds. So if somebody asks, okay, how big is Earth? How large is the radius of Earth? You can say, yeah, about 2/100th of a second. And that would be great. And this is very fundamental because this is exactly the light crossing time. When you express a length in natural units of time, you're talking about the light crossing time of that distance. This is how long light takes to get through a length of the radius of Earth. All right, wonderful. Of course, you know that in natural units of length, this is one dimensionless. So, of course, you get that the radius of Earth is the 2/100th of a second. All right, let's go with the mass of Earth. So here it's expressed in kilograms. Let me play with it a bit. Multiplying by c squared, I get it in joules. So this is the mass of Earth. Remember that in natural units, this would be one dimensionless. So that's how you get the mass of Earth in natural units of energy. Is 5.3748 10 to the 41 joules. That's the amount of energy that you would get if you transform, if you kind of get them, half of the matter of Earth is transformed into antimatter and they annihilate fully. This is the amount of energy you would release. Let's take one more step. All right, so if we multiply the mass by c and divide by h bar, we get units of length minus 1. So this is the mass of Earth in units of length minus 1. Do you recognize what this is? This is the inverse Compton wavelength of Earth. So you're expressing the mass of Earth in terms of the inverse Compton wavelength, which is something fundamental associated to Earth. When you express things in natural units, that would be the mass of Earth in natural units of length, or length minus 1, you can tell two things. Mass is different from radius, right? Radius is units of length, mass is units of length minus 1. Mass is more like an energy, units of joules, units of meters minus 1. And when you express in natural units of length, fundamental qualities of Earth, very fundamental characteristic of Earth will show up. For example, in this case, the inverse Compton wavelength. That is the mass of Earth in natural units of length. All right, let's do just another quick example with the with Newton's gravitational constant. So this is G in international units. Now let's do a little bit of multiplication by h bars and c's, and then we realize multiplying by h bar divided by c cubed, we get this expression. So it's 2.612 times 10 to the minus 70 meters squared. So in natural units of length, G is a surface, it's an area. Not only that, when you transform fundamental constants to natural units of something, what you get is fundamental scales of natural units. This is the square of the Planck length. This is the Planck area. G in natural units of area is exactly the Planck area, because that's what happens. Fundamental constants written in natural units, you will get a fundamental scale. All right. Anyway, so I hope that this gives you the flavor. I don't want to spend much time on this. I'm pretty sure you've seen this before, but just in case you haven't, this is how you convert everything to natural units. You fix one scale, say everything in natural units of length, or everything in natural units of time, or everything in natural units of energy. And you can express, using just h bar and c, you can express everything, all the quantities that you have here, you can express them in terms of one scale. Of course, you need to add more things. If you add temperature, for example, then you may need to add Boltzmann constant in there. If you have charge, you may have to add the permittivity of the vacuum. With C and H, you can already convert anything that has units of mass, energy, length, time, anything that has these kinds of units, you can convert them to one scale, only natural units of one scale, for example, length or time. And this is the way you do it. You just start with the value that you know in the units that you know, and start adding C's and H bar, powers of C's and H bar, until you get it in the units that you want, the quantity that you want in terms of energy or in terms of length. Get the Compton wavelength of the total energy of Earth, and then what you can do after that is just make one dimensionless all the fundamental constants, and then you get it. That's how you do it, and that's how you recover it as well if you want to transform from one system to another. All right, I hope that this note was helpful. If not, as usual, let's discuss in the live sessions. Now, let's do one more thing. Before we move to computing the trajectory, the equations of motion for a free particle in general relativity, let's talk a little bit about timeline curves. Because we've talked about them in special relativity, we've talked about it in differential geometry, we haven't really put them together to bring the concept to general relativity. So let's do it. What are timeline curves? Well, from differential geometry, we know that those are curves, in this case in space-time, whose tangent vector is always a timelike vector, negative norm, okay? Now, timelike curves, if you remember from special relativity, are those that are followed by physical trajectories of things with masses. They cannot be faster than light. If you go slower locally, if you go slower than the speed of light, you're gonna be following a timelike trajectory. If you remember, this is a flat space-time. You have x and you have t. Now I'm gonna use lateral units, so no c in there. If I move in this direction, I'm moving slower than light. The speed of light is 1 in natural units, so 45 degrees is exactly the speed of light. So time-like, this is a time-like vector, this would be a space-like vector. So if my tangent vector is always time-like, I never move faster than light. All right, so a time-like curve is going to be the curves that can be followed by physical objects that have a mass. Now, we can define, of course, the notion of tangent vectors with respect to different parameterization. Now, if I have a curve gamma of lambda, it will have in coordinates x mu of lambda. I can define the x circle mu with respect to some parameter lambda as the tangent vector of the curve with this parameterization. And of course, the norm of that is going to be negative. And it's going to be negative because it's a time-like vector. Again, I repeat, time-like vectors with the Lorentzian metric and the signature we chose have negative norm. All right. There is one parameterization in particular that we know of as well, that we call the proper time parameterization. In that parameterization, if you remember, we can define the for velocity like this. X dot mu is the derivative with respect to this proper time parameter of x mu. And we know that in this particular parameterization, the norm of the for velocity, the norm of the tangent vector, was minus c squared in special relativity. Well, we're going to call it minus 1 because we're going to operate with natural units. And if we want to upgrade this to general relativity, we use our dirty trick, and this is the norm of the for velocity of a curve parameterized in terms of proper time. The norm of the for velocity, what we call the for velocity here, is minus 1. All right, and that's going to be true in general relativity as well, because it has to be true locally in special relativity. It has to be true in general relativity when you do the dirty trick of getting the eta mu nu to a g mu nu. I hope that this clarifies a little bit the notion. I didn't want to jump into it without. It could be something that is very easy to most of you, but just in case, I wanted to review it. That we can export or can import, if you want, the notions of the for velocity that we saw in flat space-time in special relativity. Now we know in differential geometry we were talking about tangent vectors in terms of the parameterization that makes the norm of the tangent vector in absolute value equals to 1, and we can export or import, if you want, from the thing that is true in special relativity, it has to be true locally in general relativity as well, and that means that I can change this eta mu nu by a g mu nu, and the norm of the for velocity will be still minus 1, same as in special relativity. All right, that said, let's proceed to the calculation that I promised I would do. All right, the dynamics of a single particle, or as I would call it, let's compute again the geodesic equation from a variational principle. Let's see what we get. Let's see what a single particle does in general relativity. Now, remember what the action was in special relativity? We actually launched a set of hypotheses, right? Well, let's write the same one. The action will have to be something invariant. And what we had invariant back in the day was the line element integrated, right? So let's do the same. The line element. Let's have the action be the integral of the line element. How about that? We can add extra constants if you want, of course, like an mc squared, but remember that we're going to work with natural units from so on. And let's not add the constant. Let's just have it there because what I'm interested in is constants just factor out. I'm interested in finding the equations. All right, so first of all, let's write the line element. That's the line element. And if we want, we can parameterize it. So this is going to be an integral over, remember, this is going to be an integral over a trajectory, and we're going to find a variation on a principle. So we're going to find the trajectory that externalizes some action, this action in particular. So let's parameterize this trajectory. First, let's say that it's a time-like trajectory because that's the trajectory of physical particles. And let's parameterize with respect to a parameter lambda. Let's call it lambda to begin with. Alright, all that I did is parameter with respect to some, you can call it time parameter if you want, that moves me along the curve. The curve is going to be time-like, and therefore I know that the norm, this is the velocity vector, right? And I know that the velocity, norm of the velocity vector, which is what I'm doing here, same as we did at the end of the differential geometry block, the normal of the velocity vectors that are tangent to a time-like geodesic, they're time-like vectors, therefore the norm is negative. So the absolute value, I just put minus here. Okay, that's the same thing we did in special relativity too. Wonderful. So to find the equations of motion, we can now demand that the variation of this action is 0. So if we demand that the variation of the action is 0, that means that the variation of this integral, d lambda root minus g mu nu dx mu, d lambda dx nu, d lambda, it's equal to 0. So we compute the variation of this expression and we get this here. Of course, we're going to demand that this is equal to 0, it's Hamilton's principle, keeping the extremes of the trajectory fixed. Alright? Now, one thing that we can do is to choose this parameter lambda to be the parameter that makes the norm minus 1. That is going to be the proper time. Remember, the for velocity, when you build the for velocity, dx mu, d tau, this thing is normalized to minus 1. Alright, in natural units, of course. So, we do that. We pick the parameter lambda to be the proper time, the one that makes the normalization 1 for this. Like that, because the norm is equal to 1, I can always remove all the factors. There's a 0 in here, so the 2 is not there anymore. And we expand this variation using the product rule. And we get this expression. Variation of the first, the two others with a variation. Variation of the second, the two others with a variation. Variation of the third, the two others with a variation. Variation and derivative commute. Alright, so realize that this thing and this thing are actually the same. I can do a change of dummy indices where I can swap the mu and the nu, and g mu nu is a symmetric tensor, and these two are a product of numbers that I can commute, right? So this thing is just
twice g mu nu, d variation x mu, d tau, d x nu, d tau. That's what that means.
Now we're going to pull a trick similar to what we did for the free particle in the case of Minkowski spacetime, or flat spacetime in special relativity. I have a derivative here acting on the variation of x mu. I don't want it. I want to have just the variation of x mu. How do I get rid of that? Well, integration by parts. So we select the parts so that this thing here is du dv. So we select the parts. So this thing here is dv, and the rest is u in the separation by parts. If we do that, I'm not going to write it here because it's long, but what we will get is the part that you get from the integration by parts on this term only, this will leave as is. We apply integration by parts here, picking, I'm going to call this guy dv, and I'm going to call this and that u, alright? And I'm going to use the typical integral u dv equal to uv evaluated at the two extremes minus the integral of v du. When you do that, the two extremes are going to be the variations at tau 1 and tau 2, right? Because now we change the parameter, x mu. Let's call tau 1 the one that corresponds to lambda 1. And let's call tau 2 the one that corresponds to lambda 2, right? And that will cancel this term. This term will be cancelled in this case. So we are left with this other term, and then I take the time derivative that is hitting the variation, now hits the rest of the term. So that the one that here that is hitting the variation will hit the metric here and the dx nu d tau. That's not the variation. Let's implement that step. And that results in this expression. So to get here, I did two things. First, integration by parts on this term, right? Which gives here. You see how now the derivative is not hitting dx mu, the variation of x mu, but is hitting the rest. And here what I did is use the variational chain rule because g mu nu depends on x alpha. And if x alpha varies, is the way g would vary. So this thing here, let me just write it, is partial g mu nu, partial x alpha contracted with the variation of x alpha. Or in other words, this is the same in sorted notation, partial alpha g mu nu delta x alpha. There we go. So that's what I did there. All right, so let's word this. What I'm gonna do is I'm gonna copy this. I already used that that this are fixed. I don't need to use it again. I'm gonna copy this equation on the top, and we're gonna continue taking steps, see where we get. I know this expression was here, and instead of being erased, it moved a little bit here, and then I started and took the next step up there, just to have enough space on the board to finish the whole exercise. Now, this expression that we had, all that I did from here to here is just expand this with chain rule, right? With chain rule, this thing becomes, let's just write it here, this thing becomes the derivative of the metric g mu nu with respect to tau times derivative of x nu with respect to tau plus the metric g mu nu second derivative of x nu with respect to tau. That's what this is. Now, of course, this we can use chain rule, and we can write that this is partial g mu nu. G mu nu depends on the coordinates. Partial x alpha, and then dx alpha d tau. And of course, this I can write in short. Where is this? Here, right? Partial alpha g mu nu is precisely this term here, and this is that. All right. So let me erase this thing in the middle. And for this step, all that I did is change. Here we have an x alpha variation. Here we have an x mu. Here we have an x mu variation. Let's just take all of them x mu and take them out. So I did a swap of dummy indices on this term here, which has now become this one in the middle here for a reason, but that's the one that has become. So I did a swap of the labels alpha and mu, as you can tell. And because in this term, and because they're dummy indices, I can do it. And after doing that, I can factor out the variation of x mu. Wonderful. Now, next step. Okay, what did I do here? Well, I wrote these two terms as the sum of two terms. Instead of writing minus 2 this, I wrote as minus this and minus the same. Only that in the last term, I did a swap of dummy indices. I swapped the alphas and the nus, as you can tell here. That is pretty cool, because that means that, okay, I can multiply the whole thing by 1/2 to get rid of the 2 and get something nicer, and realize that we have a common factor. This thing is the same as this thing is the same as this thing. So we can take that common factor and write in the next step the following. So this step, of course, all that we did is multiply the whole thing by minus 1/2, and then take this as common factor and regroup the terms, right? This one corresponds to this one corresponds to this one, and this one corresponds to this one. Wonderful. So we can extract already the Euler-Lagrange equations. I can extract them because I know that for that to be 0, this whole parenthesis has to be 0. So let's extract the Euler-Lagrange equation from here, like that. Notice what I did from here to here is just equate this whole parenthesis to 0. But I also, that's why I write this here, I also multiply it by g nu beta, the inverse metric tensor from the left. So when I apply g mu beta to g mu nu, this is symmetric, right? So it's a matrix product, and this thing is the delta beta nu. So that makes this nu a beta. And on this term, I just add it, right? And then I put these two terms at the end. That's all I did. But now, do we recognize something here? Who's that? Is that Harry Potter? Is that Justin Trudeau? Actually, no, look at that. This is a Christoffel symbol. This is the covariance of the collection compatible with the metric. This freaking thing is the Christoffel symbol. That means that I can rewrite this equation as that, like the geodesic equation that we found in the differential geometry book. And of course, can be written in this way as well. So we found out of the same, well, I don't have it anymore, but out of the same action, defining the action of the free particle the same way that we did with the action of a free particle in special relativity, we found that taking from Hamilton's principle, demanding that this action is stationary and the variation of the trajectories with fixed extremes, we found that parameterizing in terms of the affine parameter, parameterizing in terms of the proper time of the trajectory, we found that the particle follows geodesics. A free particle in curved spacetimes follows geodesics. We got the geodesic equation. I need to be careful because it's late at night when I'm recording this and my neighbors may be mad. But this is amazing. Getting the geodesic equation out of the variational principle, the same one we use in special relativity, just generalized into general relativity. This is pretty cool, and this is actually the derivation that I promised that I would do when we did proper time and proper length along a curve in a Lorentzian manifold in the differential geometry block. I promised that the calculation, I gave you the result, I promised I would do the calculation later on. Here is the calculation in full detail. And yes, you see how demanding the stationarity of the variations of this action, we do get covariant derivatives. They do show up. Isn't that amazing though? I think it's amazing. All right, so now you see from first principles, if you want, physical first principles too, which of course they're geometric principles, a free particle follows the same free particle that we had in special relativity. Now in general relativity, we find that it follows geodesics. All right, of course, in flat spacetime, you get Newton's second law with no forces. But in curved spacetimes, you also have that they have to follow geodesics and they'll be subject to geodesic deviation. All right, this is all that I wanted to do in this video. I will see you in the next one where we're going to talk about actually finding out what a stress energy density is. I told you that we postulated exists, but I didn't tell you how to find it out. There's one particular case that is very important that we will actually find it out. We'll do it for a perfect fluid in the next video, and we will talk about something super interesting called energy conditions, and maybe violations of energy conditions and what they imply. Can you have faster than light travel in general relativity? Can you have it? Well, we'll see. Until then, take care.